Hey, welcome to the 28th class meeting of EECE574, the graduate level probability and random processes. As usual, homework will be assigned. And we are still here at the temporal characterization of random processes. I hope we can make a lot of progress today because we are running out of time in this semester to learn spectral characterization of a random process. Okay, so last time we studied the correlation functions, about autocorrelation functions and cross-correlation functions and cross-covariance functions. In order to talk about some properties of autocorrelation function, we restricted our interest to the random processes that have finite power. Otherwise, it's very complicated. I'm not saying that random processes of infinite power is not important. I'm saying that random process of finite power is very important. Anyway, given the assumption, which means that R sub xx sub 0 is not infinity. So this is simply expectation of x of t squared, right? So the power is finite. And then we talked a lot about the temporal properties of an autocorrelation function. For example, we've seen something like this. The autocorrelation function, suppose it's at least Poisson stationary, which means that we have a single parameter autocorrelation function. Then its absolute value is upper bounded by this ensemble averaged power of a stationary random process, something like that. To prove this one, we used the discriminant of a quadratic function. And whenever you see discriminant, remember that you are doing some kind of approximation. As you've seen in deriving the boundedness of the Pearson correlation coefficient, and also when you talked about the linear dependence of random variables or affine dependence among random variables, you always had something like this, expectation of something squared. And you wanted to minimize this one. And the linear dependence or the correlation coefficients exactly equal to plus minus 1 occurred in the cases where you have this equality. Right? Anyway, so we had a lot of properties like symmetry, conjugate symmetry, depending on whether a random process is real valued or complex valued. And at this moment, we cannot talk too much about the property of autocorrelation function because the autocorrelation function, even though it is a function of time difference or function of two time parameters, are mostly determined in the frequency domain. So when we talk about the spectral density or spectral correlation, the reason why we have some restrictions on the shape of autocorrelation function becomes clear. Anyway, so at this moment, just remember that autocorrelation function cannot have an arbitrary shape. Of course, it can be periodic, as you've seen in some very special case, which I ask you to remember. So when did you have x of t equals some a cosine 2 pi f0 t plus random variables theta, where theta is uniform on 0 to 2 pi. By the way, there is a variation of this random process. For example, instead of a deterministic number, you may have some random variable r, and that is independent of the phase. In some cases, you may see that x of t is a Gaussian random process, even though its autocorrelation function is periodic. You've seen that this random process has autocorrelation function that is a function only of tau, and it's periodic, right? So even though this is very strange random process, which is fully deterministic based on your observation in the past, it can be used to serve as a counterexamples to many misleading claims in the random processes. We also will see today, or use this today, when we talk about ergodicity of a random process. Ready? So please remember this example. It's a too important example not to be memorized. Anyway, among the properties of correlation functions, we have interest in the properties of at least wise and stationary random processes, so that we have a time difference used as a single parameter of an autocorrelation function. And as I told you, if random process is at least wise and stationary real, then autocorrelation function is real even. And if it's wise, at least wise and stationary, but complex valued, then the autocorrelation function is conjugate symmetrical. And still remember that even though not many textbooks discuss the complex valued random processes, if you are a radar engineering student, communication engineering student, then it's very, very important. So never forget. Anyway, yeah, I will not too much review about this one, but probably the handout may have this definition, but anyway, we talked about periodicity. So let me define and introduce you a periodic random process that is not deterministic. What does that mean? A continuous time signal is periodic with period t if this holds for some t positive and bounded, right? So this is the periodicity of a deterministic signal. Then what would be the periodicity of a random process? We talk with sample path. So each sample path may be periodic, right? So there are many different definitions, but one of the definition is like this. That is mean square periodicity of a random process. So this is the mean square periodicity of a random process. So we have mean squared error equals 0 for all t. By the way, given this mean square periodicity of random process X, you can talk a lot about the second order properties of this random process. So think about deriving the autocorrelation function of mean square periodic random process. Anyway, so up to last class meeting, we just considered a general random process and at least wise and stationary random process, and we studied the properties of autocorrelation functions. From today, probably to the next class meeting, we will talk a lot about so-called ergodicity, which is very, very important concept in talking about random process. So let's see. So what is the purpose of this entire course about probability and random processes in undergraduate electrical engineering and in graduate electrical engineering? So you must be able to answer to this question. And the answer is simple. There are a lot of uncertainties in electrical engineering problems to be solved. And one of the way to mathematically model the uncertainty is to use the probability theory. As I told you, there are many other ways which is not that dominant in handling uncertainty in electrical engineering. However, probabilistic approach is very important. And these days, we talk a lot about machine learning models and artificial intelligence. And probably some of you say that it's totally different from what you learn in electrical engineering. No, actually, they are almost the same. And what is done in this machine learning model, AI model, is that they want to build some inference system. And what is the inference? Inference in Korean, 추론, means that based on some knowledge, you want to make a best guess about what is not known. Okay, so in terms of black boxes, suppose here is a source that generates some unknown parameter theta. And here is another box which maps theta, which is a scalar or vector or some deterministic number after it is realized, to a random observation. So you may say that inside this box, there is a God who has two coins. One is biased, the other is unbiased. And depending on theta, God just tosses biased coin or unbiased coin. So the box has, as I shown here, a set of or class of probability distribution functions, which is parameterized by theta. Means that depending on the input data, the probabilistic distribution changes in this box, and it generates random quantity y. I just, to make everything simple, I assume the output is a random vector. It could be a random process. And this inference system accepts a realization of this random vector y. And then based on this observation, it infers, it guesses what was theta. Got it? That is inference. And there are first two types of problems. First one is that this theta is random or non-random. So there are two cases. Data could be random or non-random. What does that mean by random? They are unknown anyway. Random means that even though it is unknown, we know its probabilistic property or its probability distribution. Got it? So for example, theta is just any number, or theta is a realization of a uniform random variable on the interval 0 to 1. The story is totally different. Theta is a number between 0 and 1 is totally different from theta is a uniform random variable on 0 to 1. Because we can exploit this knowledge, the prior knowledge on the parameter, in order to make our best guess. Got it? The problem is that, as you've seen in some statistics or probability theory course, there are two persons. The frequentists say that, okay, if you go down at some level, there are parameters, unknown parameters that can never be modeled as random. But there are some people who would say that, okay, you are right. However, I will just assume this unknown parameter as a random quantity based on my assumption. Anyway, it's an approximation. If I can make a better inference system, what if the assumption is not widely accepted? As far as it performs well, it's good, something like that. So this machine learning models, for example, you want to classify whether a patient to a hospital has lung cancer or not based on its X-ray photo. You train an AI model using a lot of, for example, pre-classified X-ray photos. What does that mean? Actually, the number of photos which can be classified as lung cancer or non-lung cancer actually affects whether this machine learning model performs well or not. Just consider an extreme case. Suppose you just have given this during the training process, a single or just one non-lung cancer patients X-ray and million lung cancer patients X-ray. Then after training, this AI model would highly likely just say that whether whatever input it has, it will say that lung cancer. That is actually related to the prior knowledge that is a lot biased. Anyway, so whenever you formulate or you try to understand an inference problem, first check whether, or first ponder over whether your parameter can be modeled as a random quantity or it should not be modeled as a random quantity. That is very important. Sometimes people love this Bayesian, so-called Bayesian approach, which means that there is known prior knowledge, the prior distribution on the unknown parameter. That is very convenient. However, after you develop that some model estimator or classifier of a linear regressor or something, if you apply it to a realistic situation, sometimes you find that it totally does not work, okay? In that case, what would be the problem? Probably highly likely your assumption that the parameter is random is wrong, okay? So let me emphasize again, the unknown parameter can be modeled random or non-random. And you have to decide, okay? And then what you usually do is that using the mapping rule. In many cases, this is also very difficult. So this probabilistic mapping rule is not 100% known in many cases, okay? Anyway, so there are many difficulties even in well-formulating an optimization problem to find the best inference system. Anyway, you need to decide whether this is random or non-random, or this mapping rule has what kind of probability distribution parameterized by that theta. And another thing is this. If this parameter is a member of a set of countably infinite number of sets, then the problem is called classification problem or detection problem. If this parameter is a member of uncountably infinite set, then usually the inference is called estimation problem. And in AI models, they usually say regression problem. Anyway, so let me repeat again. First, you have to check whether you are handling a detection problem or an estimation problem. Second, whether you are handling random unknown parameter or non-random unknown parameter. After that, you also have other combinations. For example, in EECE574, which I taught on the statistical signal processing, you may say statistical inference. Because of the technique depends on what kind of observation your inference system have. So first, the problems are decided where your observation is a random vector or a sequence, which means a discrete time random process, or a waveform, which is a continuous time random process. That is also very important. But once you learn those important results and how to solve the problems with random vector observation, it is much easier to handle random sequence observation or a random waveform observation. Anyway, so there are three kind of statistical inference problems. Of course, you may have random matrix, or you may have video these days. There are many other types of inputs, but anyway, these three are most important ones. And then, as I told you, whether your problem is detection or estimation, or your parameter is Bayesian, the random parameter or non-random parameter. So at least you need to know there are 12 different problems, and they require some different techniques, or sometimes you can find commonalities among those techniques. So after you have problem, then you formulate an optimization problem to find your best statistical inference system. And then you solve the problem, and then you analyze the performance of your inference system. So if you do a graduate study, sometimes you focus on this performance analysis. So given a communication system, given a specific receiver, how can you parameterize the system's performance as closely as possible, but with only a few of parameters, something like that. So performance analysis is very important. Sometimes solving the problem is very important. In many open problems, some famous researchers have found some of the solutions. There are many optimal solutions in some problem. They provide some of the optimal solutions which they could find. And for example, it has very high complexity. Then could there be any suboptimal solution that is very close performance to the optimal, but has much lower complexity, something like that, when you make an inference? So this is all about actually the statistical signal processing courses first day. But here, let's go back to our problem in this course. So we want to do some statistical inference. That's why we have this course. Now, in the context of learning random processes, we have a problem. The problem is that we only have, so this random process, suppose this is our observation, then sometimes if we assume that it's a continuous time random process, what do we have here? A lot of sample paths in the ensemble, right? So you have the sample space, event space, and probability measure. And if outcome S comes out, then here, depending on S, this random process, which is a mapping rule, chooses a sample path to be realized, right? So, and also these functions are defined as a function on the entire real line. Of course, this negative and positive infinity may mean for sufficiently large future or sufficiently large past. But anyway, in order to rigorously model using this mathematical tool, you have to have some way to pass through or circumvent this logical problem of the fact that you can observe only a single sample path given this continuous time random process model. So it's like you are given some specific sample path. And can you make any statistical inference? So given a random process observation, can you make any statistical inference? So statisticians have thought about this problem, and they found, or they defined, a subclass of random processes called ergodic random processes. And this ergodic random process solves a lot of trouble from the fact that you can observe only a single path. The idea is very simple. So even though we observe a single sample path, we can do statistical inference. Now let's see what is the basic of statistical inference. Anyway, we have to be able to handle probability of some event, as I told you in the first class meeting. Probability of event is one of the most important phrase in this course. Then what is the probability of a certain event? Now, at almost the end of this graduate course, statistical inference is related to the probability of some event. And what is probability? As I was shown here, wrote here, probability of event that your observation, for example, X, is in some set, which is the event, that can be always rewritten as expectation of an indicator function specifically chosen like this, subscript A of capital X. So remember this, statistical inference is all about finding some probability, usually finding posterior probabilities. And as you will see in statistical signal processing, especially when you handle Bayesian problems, the posterior probability of the parameter given the observation is a sufficient statistic, which means that that is what you need to handle in order to make any statistical inference for Bayesian problem. Of course, for the non-Bayesian problems like parameter theta is just unknown, you have something similar to posterior probabilities anyway. So in order to make statistical inference, handling probability of some event is important. And as you've seen in the link between the expectation and probability, probability is a mere an ensemble average. So the idea is simple. You need to replace ensemble average by something in order to make a statistical inference given a single sample path. That is the motivation. So people assumed that what if we define this assumption like this? Even though we observe a single sample path, from the single sample path, what if we may know or we may derive the property of ensemble average? And that notion was very complicated when I first saw this one. So let me skip and go to this one, okay, this example. So suppose you have a Poisson random process. You know what is the sample path, right? From the origin, this is time axis, this is number of count axis, and your sample path jumps by unit, and it is a right continuous function. Now, how many parameters do you need to fully characterize a Poisson random process? Just the arrival rate, lambda, right? As you know. Now, let me ask you a question. From a single sample path, can you find this arrival rate? Right? So this single sample, the arrival rate fully characterizes the ensemble, which means that, for example, if I give you some set of sample patterns of this Poisson random process and ask you, how is it probable that a sample path is a member of this subset? For example, this subset may have only one sample path that is 0 for million years, right? And I give you a sample path 1 that is fully realized. And you may, it may be complicated. So it's like this. So I provide you, so you are given single sample path. So something like this. You don't know what is S0, but anyway. And I ask you, how probable NT S1 0 for all T? Got it? And this is related to the arrival rate. For example, you know what is the arrival rate, lambda. Then when is it highly likely? Lambda equals 0, right? If lambda equals 0, this will occur with probability 1, right? However, if lambda is any non-zero positive value, the probability of this observation, all 0 observation occur, is 0, right? Got it? So what I'm saying is that given a single sample path that has some progress, then can you make this, can you find this probability, right? Can you make this inference? And your answer is yes, because of this one. So in the handout, I mistakenly put expectation, but remove that, okay? So here, let's define lambda hat as the random process evaluated at time capital T divided by time capital T. So by choosing this capital T, you have different random variable, right? As I told you, if you sample a random process, you have a random variable. You have a random variable divided by a constant, you still have a random variable. But depending on the choice of this capital T, you have different random variable. Now, what if this T is very, very large? So what will happen? And that is the idea. So first, let's see. You know, since n of capital T is a Poisson random variable with parameter lambda times capital T, its mean ensemble average is lambda T, and its variance is also lambda T, right? As you've seen already. And also, this is interesting thing. Expected value of lambda hat is lambda. Why? Because expectation of this one is lambda capital T. So divided by T becomes lambda. What is the variance of this lambda? The variance is what? See that? Variance of NT, that is lambda T, divided by T squared. So you have lambda over T, right? Now, what is lambda hat minus lambda squared? And then you take the expectation. And from this, you have lambda over T that tends to 0 for sufficiently large T, right? Now, what does this mean? For sufficiently large T, this random variable has mean lambda and variance infinitesimally small. What does that mean? It's almost a deterministic number. So whatever realization you have, right? Whatever realization you have, for sufficiently large T, your lambda hat can be used as a good estimate of the arrival rate. Because variance is 0 means that you have a deterministic number, not a random variable. So this shows that the Poisson random process is parameterized by a single parameter lambda, and it can be inferred from a single realization. this single realization has what? Of course, from 0 to infinity, right? So if you choose very large number, and that value divided by that time instant will give you almost accurate, exact arrival rate. Got it? And then what can you say? Given other realization, some other sample path, and I may ask you, what is this sample path likely to happen, as I just said? And you've seen that your given sample path evolves from 0, and then lambda must be non-zero. In that case, all 0 probability is 0, right? So this example shows you something interesting. Even though I may be given a single sample path of random process, I can fully characterize this entire random process, because this random process in this case is fully parameterized, by single parameter lambda. And I know what is lambda with very accurate, very small error. Got it? So let me repeat you. A single sample path may provide you full characterization of a random process. An interesting thing is that this Poisson random process, is it stationary? No, because its mean path is lambda t, right? Which means it is not wise and stationary. So it cannot be stationary at all. So even though this Poisson random process is a non-stationary random process, its single sample path provides us a lot of information. In this case, full characterization of the random process. So there is an example like this. So why not? Let's define some subclass of random process, subset of random processes where we can do something like this. Got it? And that is the idea of ergodicity. Ergodicity means that actually, from a single sample path, you can know something about the full ensemble. You can guess something about the underlying probability space, or you can guess something about that random process, which is the mapping rule from S to the sample path. Got it? Unfortunately, ergodicity is in many cases is assumed, defined like this. Time average can be replaced by ensemble average, which means that we need ensemble average to make statistical inference, right? Probability is an ensemble average, expected value of something, right? However, we can't compute this ensemble average or statistical expectation. So people have defined a subset of random processes where we can replace ensemble average, statistical expectation, with some time average. Of course, if we restrict the ergodicity to this level, that Poisson process is out of this set. However, so what I want to say is that there are many different levels of ergodicity, which means that in more general sense, ergodicity means that from a single sample path, you can fully or partially characterize the entire ensemble. But in a narrow sense, that is most cases, time average can replace some, not every, some statistical average in the statistical inference. That is ergodicity. So let's see something more. We go back to our friendly example. Y of t equals some random variable r times cosine 2 pi f0 t plus uniform, continuous uniform theta. Now, suppose I have given you a single realization of this random process. Then let me ask you, can you guess what is the random variable r and what is the random variable theta? Any idea? Well, what if I just tell you that theta is uniform, but R is some random variable, of which distribution is fully unknown to you? Can you make any inference? So here are two problems you have to distinguish. See that? I give you a single realization and ask you predict this sample path. So even I do not provide the entire sample path. I provide you the part of the sample path. So x of t is the sample path, but I give you from 0 to capital T. So part of it. Oh, sorry, not this. Right? After I generate R and theta, it's a deterministic function, but I give you only on this interval, 0 to some capital T. Now I ask you, so this is x t of some s0, right? And I ask you, what is the value of this sample path at 2 capital T? So at this time instant. Can you make a full prediction? Prediction is also what? Related to expectation, right? Sometimes it is a random variable, sometimes a single number, which has variance 0, but usually it's distribution. But anyway, so given the part of random process, can you predict the value out of this time window? But be careful. Here, I ask you that this sample path at time t equals 2t. And your answer is that, yes, I can perfectly predict, because given a single realization from some non-zero interval, you can perfectly know what is the realized R and theta. Then just find R and theta and evaluate R cosine 2 pi f0 times 2t plus that theta will give you the exact prediction of this realization, right? It's obvious, but be careful in the second problem. Now I ask you something like this. So I give you a single sample path, but only on some specific interval, 0 to capital T. And I ask you, what is the random process at 2t? This means actually, I ask you, what is this one? And you now know lowercase x of 2t and capital X of 2t are different. This is what? This is a number. This is what? A random variable, right? So I ask you, what is the probability distribution of this random variable? After I give you part of a single realization. Can you make any inference? Of course not, right? So in this question 2, your answer is that I cannot make any guess, right? So it's different. Anyway, so there are different cases like this. First, from a single sample path, sometimes you can extract the information about the entire sample path, sometimes, like Poisson random process as a given, right? Sometimes, given a single sample path realization, I can extract some information about some subclass of ensembles. In the worst case, from a single sample path, I cannot extract any information, as we've seen, right? That capital R cosine 2 pi f0 t plus theta give you perfect value for specific sample path you've observed. However, it does not provide any information of the entire ensemble. Got it? So be careful. Okay, here goes the kind of definition of ergodic random process. Among many random processes whose single sample path provides some information about the entire ensemble or some part of ensemble, ergodic random processes in a narrow sense is defined like this. From the time average of a single sample path that is given to you, you can extract some information about the entire ensemble. And especially by replacing the ensemble average with that time average. The problem is that we didn't define what is time average exactly, even though you already know. So here goes the definition of time average. First, suppose you are given a deterministic function x of t. What is the energy of the signal? Of course, energy requires some scaling, even though you square the signal. But in electrical engineering, the convention is that when you are given a function that models an electrical signal without any context, the energy is defined as this. You square it, or you take the absolute value and square it, and then you iterate for a sufficiently large interval, sometimes for infinity. That is defined as the energy of the signal. Got it? So here, this is the energy. And what is the power? Power of a signal is defined similarly, but usually in physics, power is what? Energy divided by the time interval. So power of signal could be defined as energy computed on this interval negative t to capital T divided by the length of interval. But this is a power on the specific interval, but without specifying the interval, we take the limit of this integral. So we let t tends to infinity, and if this value converges, then we call this as the time average, the power of the signal. Now, from this power definition, we define the time average. So it's like this. We view the power as time average, which is the limit 1 over 2t from negative t to capital T and something t. And something is instantaneous power. So we have a notation like this, capital A of something. Capital A of something means that limit at t tends to infinity, 1 over 2t, something dt. So this argument is instantaneous power, then you have what? The time averaged power. Got it? So here goes the definition. This is the average of x of t. This is the average of instantaneous power, which is power in our normal definition. And what we are going to do is that we want to replace statistical average appearing in handling random processes with time average. The problem is that it is not obvious when we can do that replacement. So let's take a look at the simplest expectations first. So given a random process x of t, for example, continuous time random process, what is the ensemble average you mostly use? First one would be, of course, the expectation of x, right? Which is a function of t in general. Second, what would be the ensemble average? The autocorrelation function. Right? So if there are some classes of random processes where ensemble average can be replaced by, the ensemble average can be replaced by time average, probably this ensemble average could be replaced by time average, or this ensemble average could be replaced by time average, right? So we start from this one. The problem is that given a single sample path, if we do time average, then can we get a time function of time at all? No, we can't. So think about this one. Consider time average of a single sample path. What is that? Is it a function of t? No, it is not, because it's simply a scalar. So in order to define or talk about ergodicity in terms of the mean ensemble average of the random process is replaceable by a time average of single sample path, the random process must have constant mean, right? Otherwise, it does not make sense. So we find that, okay, we need this one. Mean must be constant in order to talk about narrow sense ergodicity, right? Second, again, now let's focus on this second order correlation. Again, we see that, okay, then I may think about the time autocorrelation function of a sample path, single sample path, which is defined as what? Limit x of t plus tau x conjugate t dt. And as you see here, if you just compute the time average instead of ensemble average of entire ensemble, if you take single sample path and take the time average, you have what? A function only of tau, right? So this is a function only of tau. So these two are not functions of t. What does that mean? Again, here, in order to talk about the ergodicity, we need to have t disappearing. What does that mean? In order to talk about ergodicity of a random process, we need y-sense stationarity first, right? At least y-sense stationarity. Otherwise, we can't talk about ergodicity at all, right? That is so far so good. So, okay, in order to talk about ergodicity, we may need at least y-sense stationarity. Good. But is it really true? But before we discuss about that, let's see more property about this time average. And this is really confusing. I also got confused a lot. Okay. First thing is this one. What if you are given a constant function and you want to compute the time average? So your function is equal to some constant c for all t. What is the time average? If you use the definition, or if you use the intuition, then time average is that constant, right? So far, so good. Now, suppose you are given some function that is a power signal. What does that mean? Power signal means that your time averaged power is strictly positive, not zero, but finite. Okay? And you can easily show that if a signal is a finite energy signal, its power is zero. So it can never be a power signal. Got it? And if a signal is a power signal, its energy is infinity. It's obvious because you divide the energy by the time period. And in most of the cases, when you compute the energy of a signal, if you compute the power signal, especially when you compute the power of a signal, you have the limit operation. Now, the question is that integration interval matters? Here, I intentionally chose negative capital T to positive capital T. Is it necessary? Can I just do something like instead of integrating over negative t to positive t, can I just do something like this? So I have offset by capital T. Are they the same? And we know that by intuition, and you can prove that if the left-hand side exists for some signal, so this is time average of some signal x. If the left-hand side exists, the right-hand side exists, and they are the same. What does that mean? This integration interval, as far as it covers the entire band, actually, and also it's important to have the same rate because there are strange signals. But anyway, so this is translation invariant. And as you remember, translation invariance is related to time invariance in system, and in random process, stationarity. So it appears that you want to say that, okay, ergodicity is a special kind of stationarity, right? However, even though many textbooks really says that, undergrad textbook, I really object. Why? As I've shown you already, given a Poisson random process that is not stationary at all, right? You can perfectly estimate lambda from a single realization. So stationarity and ergodicity are related, of course, especially when you want to talk about replacing the ensemble average with time average. You require the process to have constant mean and constant autocorrelation first, right? So your time average, your stationarity and ergodicity is closely linked, but they are different. That's why I have shown you the block diagram, the Venn diagram, Venn diagram like this. The set of all random processes, and here's stationary random processes, and here ergodic random processes. Of course, the intersection is non-empty set. That's why we defined this stationary and ergodic random process. And by the way, if you take a look at a lot of research papers, yes, usually they have some theorems like this. If X is stationary and ergodic, then blah, 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 blah. Got it? They are not just saying that it's stationary, then blah, blah. They need ergodicity to make statistical inference. So remember this, even though the time average appears that some stationarity is satisfied, the ergodicity is kind of subset, but it's not exact. Of course, if you restrict a lot, then you may have some very narrow sense ergodicity. In that case, you have something like this, stationary and ergodic. Got it? So in a very, very narrow sense, ergodicity is a special kind of stationarity. However, in general sense, then this Venn diagram is much better. Okay, so either one is basically correct. However, don't just think this is the only Venn diagram used to define ergodicity, even though many textbooks says that. Okay, now let's think more about this time average over random process. Okay. I talked about the time average of a specific sample path or a deterministic function. Now I'm talking about the time average of a random process and ask you what it is. What is it? So let's use the definition. So time average of capital X of t, which is defined as the limit 1 over 2t integration of x of t dt. What is this? Whenever you have confusion, then go back to our graduate level definition of random process. Then this one is actually that one, right? As I told you, we, for convenience, just drop parenthesis s to denote random variable, random vector, random process. So whenever you have difficulty, then replace this one like this. Now, the integration, this limit of integration becomes more clear. Limit 1 over 2t, integration of this one. Now, you integrate over t. Then, what is it? It's a function of s if it converges, right? Now, you have a function of s, and what is s? S is the outcome from your underlying probability, underlying random experiment. You have a random experiment and a measurable function of s. What is it? Random variable. So this is what? That is what? A random variable. So time average of a random process is a random variable, but you observe a single realization of the random variable if you compute the time average of a single sample path. Got it? This is similar to you just observe a single coin tossing result or rolling dice result. So as you see here, even without taking the limit, what is this one? This is a function of s, which is a random variable. Now, this random variable is parameterized by capital T. So by changing capital T, you have what? Uncountably infinite number of random variables. And you have, if you take T as, for example, 1, 2, 3, 4, 5, 6, right? If it converges, then you don't need to take continuum. You can choose just integers, for example. Then you have what? Limit of at least the sequence of random variables. And it converges to a random variable. So again, our knowledge learned in this course, in this graduate level course, about the convergence of a sequence of random variables kicks in. So when we talk about the fact that the time average of a random process is a random variable, in order to specifically talk about that, we have to specify what kind of convergence mode we are interested in, right? Because this is, here we are talking about the convergence of a sequence of random variables to another random variable. Of course, there are 4 modes of convergences, which we are mostly interested. But in this course, and in many cases, because we want to relate the statistical average with time average under the ergodic assumption, we talk more about the convergence in the mean square sense. Got it? So let me remind you, when you have a sequence of random variables xn, what does that mean by the sequence converges to another random variable in the mean square sense? Very simple. You take the error and compute the mean squared error. If that goes to 0, then xn tends to x in the mean square sense. And to make the notation simple, we introduce this one, limit in the mean. So the limit in the mean of xn equals x. What does that mean? Xn converges to x in the mean square sense. And we will talk about a lot about mean square convergence and mean square ergodicity. Okay. So first, we talked about the time average of random process. Now, what about the time average of a random process x evaluated at t plus tau times the random process evaluated at t conjugate? So this one. What is this one? Time average of x t plus tau times x conjugate t. Again, if it confuses you, I ask you to replace this time average like this. Okay, so this notation is really convenient, whether t is continuous time parameter or discrete time parameter. So this t plus tau appears here, and parenthesis s means that you are using measure theoretic approach to talk about the random process, not as some continuous time or discrete time signal with uncertainty. You just view random process as a mapping rule. Now, you just use the definition. So here, limit 1 over 2t, integration over negative t to capital T. And here goes what? Function parameterized by t, tau, and s. But it is integrated over t. Then what do you have? You have a function of t and tau, tau and s, right? So let me just use this way. This R is not capital R, it's kind of calligraphic letter R, XX, and parameterized of tau and s. Now, whenever you have something parameterized by s, that is the outcome of this underlying random experiment, then you have random something. Okay? So what is that? It's a random function of tau, random function of tau. So what is it? It's a random process, if you want to call it a random process. Got it? So your time autocorrelation function of a random process, not a sample path. Time autocorrelation of a random process is a random process. Now again, let's fix capital T. Then what do you have? You have a sequence of random variables when you fix tau, okay? Random variables that converges to a random variable. So if you fix tau, then you have random variables and a target random variable. So again, the limit must be chosen to mean one of the modes. Again, let's assume that we prefer mean square convergence. What does that mean? Limit in the mean of the integral converges to something. Now, so far, so good. So we kind of have so-called build up for this discussion. So our target is to replace the ensemble average with time average. So in order to understand that, we studied time averages so far. Now, what is this time average autocorrelation function? As I told you, it's a random variable parameterized by tau, right? Since a random variable can be partially characterized as mean, why not computing the ensemble average of time average? Of course, our objective is to replace ensemble average with time average, not ensemble average of time average. Be careful. However, it would not hurt us much to think about ensemble average of time average. What do you think about that? So let's compute it. So before we talk about ensemble average of time autocorrelation, let's talk about ensemble average of time average of T. So this one. And then let's think about that one. And as I told you, this time average, without taking the expectation, is a random variable, right? So you have a random variable, and interestingly, if you take the expectation and if we assume that the order of expectation and time average can be changed, then we have this one. Statistical expectation of x of t, which, what is that? It's a function of t, deterministic function of t, then time averaged. Right? So this is a function of t in general. What if we have at least the stationary random process, Poisson stationary random process? This expectation is already give you a deterministic value. So time average doesn't matter, as I told you. If you have a constant function, time average of that constant function is the function value, right? So as I told you already, in order to talk about this ergodicity, we need at least Poisson stationarity. Now let's think about the ensemble average of time average of autocorrelation. Time averaged autocorrelation. Again, let's assume that expectation and time average can be interchanged. Then here, what do you have? This is what? This is the autocorrelation function of random process. In general, this autocorrelation function is a function of t and tau, right? So after we compute the time average over what? Over t or tau? Over t, right? Time average over t, we have function of tau. But what if this is already Poisson stationary? Then it is not a function of t, so this time average disappears. Be careful. In general, I'm not saying that the time average of, the ensemble average of time average equals ensemble average. I'm not saying that. I'm saying that if the ensemble average of time average equals ensemble average, if the random process is at least Poisson stationary. Got it? Now let's see some counterexample, or example if you want to say. So consider this random process, very simple random process. You toss a coin, and depending on whether it is tail or heads, the output sample path is either a constant 1 or 0. Sorry, constant 1 or negative 1. Got it? So if your outcome is heads, then or 1. If your outcome is tails, then or negative 1. Now, given this simple random process, let's check whether this time average and ensemble average how they are related. By the way, let me ask you a question. Is this random process a kind of ergodic process? Which means that from a single realization, can you extract some information about the ensemble average? No. Why? Your sample path is either all 1 function or all negative 1 function, right? Then how can you know about the ensemble average? For example, there could be some another random process that may be defined as some constant x of t equals c, but that c value is determined by a uniform random variable from negative million to positive million. And you happen to observe x of t equals 1. Then can you say that, okay, I've observed all 1 random process. Now let me guess the random process x of t equals 2 million times theta, 2 million times u is 0, 1, minus 1 million. Can you say that? No. So this random process is not ergodic at all. Now let's see, what is the time average of the random process?
Dr. Joe, it is time to wrap up. Dr. Joe, it is time to wrap up.
It is either 1 or -1, right? What about the time autocorrelation function? Of course, it's either 1 or -1. What about the ensemble average? 0 for all t, right? What is the autocorrelation function? Ensemble average autocorrelation function. 1 for all t and tau, right? Of course, this is a random variable, and that is a random variable with probability 1/2 and 1/2, 1/2 and 1/2. So you must remember this. Ensemble average cannot be replaced by time average in general, right? Because this is random variable, and this is, in this case, these are constant functions. However, under the ergodicity, we assume or we restrict our random process as a class of random processes where ensemble average can be replaced by time averages. And let me go back to the first part of today's lecture. Why do we do that? In order to do some statistical inference. Got it? Because we observe a single realization, but we want to talk about the probability, expectation of something. Without assumption like ergodicity, we can't make any statistical inference. So it's kind of, in Korean, 필요악. So we need this assumption to make statistical inference. Okay, that's all for the day, and let me continue next time.